Let's graph and transform the natural log function, or f of x equals the natural log of x. And when we write ln, remember the implied base is e. Here is the graph of our natural log function, and we can see that there is a vertical asymptote at x equals 0, which is the y-axis. We can see that there is an x-intercept at 1, 0. The domain is from 0 to infinity, or x value is greater than 0, or the set of all x's such that x is greater than 0. And the range is from negative infinity to positive infinity, or y is an element of the real numbers, or the set of all y's such that y is an element of the real numbers. So I do want to point out a relationship between the natural log function and f of x equals e to the x. So to see that relationship, let's take our natural log function and find its inverse. So remember, to find the inverse, we'll change f of x to y. We will swap x and y, so now I have x equals the natural log of y. And to get y by itself, we will rewrite this in exponential form, remembering that our base here is e. So e to the x equals y, or f to the negative 1 of x, or the inverse of f of x equals e to the x. So the natural log of x and e to the x are inverse functions. And to remind you, f of x equals e to the x has the following attributes that are similar but different from the natural log function. So f of x equals e to the x does not have a vertical asymptote. Instead, it has a horizontal asymptote at y equals 0. It does not have an x-intercept. Instead, it has a y-intercept at 0, 1. And the domain and range are swapped. So the domain is all real numbers, and the range is from 0 to infinity, or y is greater than 0. So there is a relationship between these attributes because these two functions are inverses. Okay, let's look at some graphs of the natural log function. So we're going to look at y equals the natural log of x, y equals 3 times the natural log of x, y equals 1/3 times the natural log of x, and y equals negative natural log of x. We can see all 4 of these graphed on the same coordinate plane here. The parent function is graphed in black, and I will remind you of some of its attributes. We have a vertical asymptote at x equals 0, an x-intercept at 1, 0, a domain from 0 to infinity, and a range of all real numbers. And in red, we can see the graph of y equals 3 times the natural log of x. This is a vertical stretch by a factor of 3. And there is no change in any of the attributes. All of the attributes that the parent function had, the vertical asymptote, the x-intercept, the domain and range, remain the same for y equals 3 times the natural log of x. In blue, we see the graph of y equals 1/3 times the natural log of x. This is a vertical compression. And again, there is no change in the attributes from those of the parent function. Finally, in green, we see the graph of y equals negative natural log of x, which is a reflection over the x-axis. And once again, there are no changes in the attributes that we had for the parent function. So in summary, for vertical stretches, compressions, and reflections, if we have a function of the form y equals a times the natural log of x, if the absolute value of a is greater than 1, we have a vertical stretch. If the absolute value of a is between 0 and 1, we have a vertical compression. And if a is less than 0 or a is negative, we have a reflection across the x-axis. Okay, let's look at a few more graphs. This time we'll look at y equals the natural log of x, y equals the natural log of x plus 3, and y equals the natural log of x minus 2. Here we can see all three of these on the same coordinate plane with the parent function graphed in black again. And the parent function has the attributes that has a vertical asymptote at x equals 0. It has an x-intercept at 1, 0. It has a domain from 0 to infinity. And it has a range of all real numbers. In red, we see the graph of y equals the natural log of x plus 3. This is a vertical translation or shift up 3 units. And the only attribute that changes from those of my parent function is the x-intercept. So the vertical asymptote remains the same, the domain and range remain the same, but the x-intercept for this red function becomes 1 over e cubed, comma 0. And I found that by remembering that to find the x-intercept, we substitute 0 in for y. So I ended up with the equation 0 equals the natural log of x plus 3. I want to get my natural log by itself, so I'm going to subtract 3 from both sides, and I get negative 3 equals the natural log of x. And then I will convert this to exponential form. Remember, natural log has a base of e, so e to the negative third power is x, and e to the negative third power is the same thing as 1 over e cubed, which is where my x-intercept came from. Here in blue, we have the graph of y equals the natural log of x minus 2. And this is a vertical translation or shift down 2 units. And again, the only attribute that changes is my x-intercept, and it becomes e squared, comma 0. And again, I found that by putting 0 in for x. So we have 0 equals the natural log of x minus 2. If I add 2 to both sides, I get 2 equals the natural log of x. And we'll convert this to exponential form. Our base is e, so it becomes e squared equals x. And that's where my x-intercept came from. And then in summary, for translations, for vertical translations, if we have a function of the form y equals the natural log of x plus d, when d is greater than 0 or positive, we have a shift up the absolute value of d units. When d is less than 0 or negative, we have a shift down the absolute value of d units. Okay, let's look at a few more graphs. We have y equals the natural log of x, y equals the natural log of x minus 3, and y equals the natural log of x plus 2. Here we can see all three of these graphs on the same coordinate plane with the parent function graphed in black again. And the attributes of the parent function are vertical asymptote at x equals 0, an x-intercept at 1, 0, a domain from 0 to infinity, and a range of all real numbers. In red, we can see the graph of y equals the natural log of x minus 3, which is a horizontal translation or shift right 3 units. And several things will change in terms of attributes. So with the parent function, we could see that there was this vertical asymptote here at x equals 0. But when we shift left 3 units, you can see that our red function has a vertical asymptote at x equals 3. And the x-intercept also shifts right 3 units to 4, 0. And because the vertical asymptote shifted, our domain changes to 3 to infinity, or x value is greater than 3. In blue, we see the graph of the natural log of x plus 2. And again, a few attributes will change. This is, again, a horizontal translation or shift. This time we are shifting left 2 units. And our vertical asymptote shifts left 2 units to x equals -2. Our x-intercept shifts left 2 units to -1, 0, and our domain changes to x values greater than -2. So in summary, for horizontal translations, if we have a function of the form y equals the natural log of x minus c, when c is greater than 0 or positive, we are shifting right the absolute value of c units. When c is less than 0 or negative, we are shifting left the absolute value of c units. So finally, let's look at 3 more graphs on the same coordinate plane. We will look at y equals the natural log of x, y equals the log base 2 of x, and y equals the log of x, which is base 10. Here we can see these all on the same coordinate plane. So we have the natural log of x in black, we have the log base 2 of x here in red, and the common log base 10 of x here in blue. So our bases are e, 2, and 10, and the 2 is the smallest base that we're looking at here. 10 is the largest base, e is between the two of them. And in general, so for a log function, y equals log base b of x, b does need to be positive. These are all positive numbers, all of the bases we're looking at. And b does not equal 1. And the larger the b, so when we look at log base 10, which is the largest one we've graphed here, the slower the function seems to grow. All of the bases that we're looking at here are greater than 1, and the function grows from left to right. If the base was between 0 and 1, the function would decrease from left to right. Let's look at what that could look like. So if I took a base that was between 0 and 1, let's look at base 1/2. So y equals log base 1/2 of x. I still have an x-intercept at 1, 0. I have the point 2, -1, 4, -2, 8, -3. I have 1/2, 1, 1/4, 1/4, 2. And if we sketch that in, here is our graph. And you can see it's decreasing. So that is anytime we have a base between 0 and 1.